Okay, so this is part two of our discussion on the interaction between operating systems and computer architecture. And hopefully we don't have too much spalling noise today, but if we do, I'll try to speak a little bit louder as I do this. Anyway, welcome, and this is chapter 8, part 2, if you're following along in the text. So last time we talked about unit programming and multi-programming environments. And for unit programming, we just basically split the memory into the operating system and the current program being executed. In multi-programming systems, the user part of the memory gets divided into multiple processes to accommodate all the different things that are running. And so memory management is the task of the subdivision. We have to allocate memory as efficiently as possible to pack as many processes into the memory as we can so that we can swap them out and make efficient use of system resources. And the problem, an idle processor is the devil's plaything. And we discussed three types of queues that we use for processes. One is the long-term queue of requests for new processes. There's the short-term or dispatcher processes that are ready to use the processor, and various I/O queues of processes that are not ready to use the processor. We need this since the I/O activities are usually much slower than computation, and the processor in a unit programming environment is generally idle most of the time. Even multi-programming doesn't solve this, since the processor can still be idle if all the processes are waiting for I/O. So, what's the solution? Well, one solution is more RAM, and you can certainly attempt to download some. Seriously, one solution is to expand the amount of memory. The problem is memory is expensive, despite what it says here on this little infographic. Programs also tend to expand to make use of as much memory as you have. If you're working with things like Unreal Engine, Adobe products, they certainly expand to consume all the memory that you have. So that is one solution, but there is a limit that you're going to bump up against given the current architectures. Another solution is swapping. And so rather than remaining idle, the processor will swap one of the processes that's active in memory back out to the disk to an intermediate queue. The OS can then bring in another process from the intermediate queue to the short-term queue, or it can honor a new process request from the long-term queue. Execution then can continue with the newly arrived processes. And the intermediate queue is a queue of existing processes that have been temporarily kicked out of memory, but not yet terminated. But swapping can sometimes make things worse. It's an I/O operation, and again, I/O tends to be a bit slower. It has the potential for making the waiting for I/O process better, not worse, but there's some good news. One, disk I/O is generally the fastest I/O on a system, and swapping usually does enhance performance with tools such as virtual memory partitioning and paging. So let's look at partitioning. So the easiest one is a fixed size partition, and basically partitions don't have to be of the same size, but we have to set them aside as a fixed amount. And when a process is brought into memory, it's placed in the smallest available partition that'll hold it. It could still be wasteful of memory. We could have, a 3 megabyte process, but have to put it into a 4 megabyte partition, which would waste 1 megabyte of potentially usable memory. So, one solution is variably sized partitioning. When process is brought into memory, it's allocated exactly as much memory as it requires and not a bit more. It starts out well, but you can end up with a lot of holes in memory. One way to deal with this is compaction, which will help deal with the fragmentation of the memory. But again, to clean that up, it consumes time. And from time to time, the OS will shift the processes of memory to place all the free memory together in one block, and that's what compaction is. It is time consuming, and it can waste some processor times. The other thing to consider is the address problems. And the process is not likely to be loaded into the same place in main memory each time it gets swapped in. And if a compaction is used, the process may have been shifted while it's in main memory. So a process in main memory consists of the instructions plus the data, and they will contain addresses for memory locations of 2 types, data items and instructions used for branching instructions. Moving these about has the potential to create problems because you're shifting addresses when you move things about in main memory through compaction. To solve this, the distinction gets made between logical addresses and physical addresses. Logical addresses expresses location relative to the beginning of the program, and the physical address is an actual location in main memory. When the processor executes the process, it automatically converts from logical to physical address by adding the current starting location of the process, called the base address, to each logical address. Another tool in our arsenal are frames and pages to make as efficient use of memory as possible. And both the unequal fixed size and variable size partitions still have some inefficient uses of memory, whether that's wasted memory or holes or the need for compaction. But suppose memory gets partitioned in equal fixed size chunks that are relatively small. Each process also gets divided into small fixed size chunks of some size. We now have pages and frames. Pages are the chunks of the program, and frames are the chunks of memory. And then we can assign pages to frames. With frames and pages, you can still load a process even if there's not a big enough contiguous frame, because you can do it across multiple frames. The OS maintains a page table for each process that shows the frame location for each page of the process. And this approach solves the problems raised earlier. Main memory is divided into many small equal-sized frames. Each process is divided into frame-sized pages. Smaller processes require fewer pages, and larger processes require more. When a process is brought in, its pages are loaded into available frames, and a page table gets set up. Demand paging is where each page of a process is brought in only when it's needed, and this uses the principle of locality. When working with large process, execution may be confined to a small section of the program, like a subroutine, and it's better use of memory to load in just a few pages rather than load in the entire thing. If the program references data or branches to an instruction on a page that's not in main memory, we get a page fault, which tells the OS to bring in the desired page. So some advantages of demand paging are more processes can be maintained in memory. We save time because unused pages are not swapped in and out of memory, and it's possible for a process to be larger than all main memory, so you don't have to keep track of how much memory you have. When one page is brought in, another page must be thrown out. That's a page replacement, and we're going to talk about some of the ways that you can do that. If a page is thrown out just before you're about to use it, then the OS will have to get the page again, and that can lead to something called thrashing. And thrashing is when the processor spends most of its time swapping pages rather than executing instructions. In the old days, if you had a mechanical hard disk, you could actually hear it clunking and going back and forth to bring things in and out of memory. Page fault is if a program branches to an instruction that's not in main memory, or if the program references data on a page that's not in memory and you have to bring it in. And page replacement is when a new page is brought in, you need to take out an old one. So which one do you take out? So the page table is held in main memory when accessed. You need to have a register to hold the starting address of the page table for the running process. In most systems, you have one page table per process, and to avoid storing all of them in main memory, you can store them in virtual memory using a two-level structure. That is, the page directory points to a page table. And there are further enhancements that are possible with the use of inverted page table structures. And pages 300 to 301 have the details on that. The other thing that you have with the paging systems is the translation lookaside buffer. And so every virtual memory address can cause two physical memory accesses, one to fetch the appropriate page table data, and two to fetch the desired data. A straightforward virtual memory scheme would have the effect of doubling the memory access time. To overcome this problem, most virtual memory schemes make use of a special cache for page table entries, usually called the translation lookaside buffer. And that functions in the same way as a memory cache, and it contains those page table entries that have been most recently used. And by the principle of locality, most virtual memory references will be in locations in most recently used pages. So we end up with most references that involve page tables that are in the cache. Segmentation, this is an aspect of it that is usually visible to the programmer. It's provided as a convenience for organizing programs and data as a means of associating privilege and protection for the data. And it allows the programmer to view memory as consisting of multiple address spaces or segments that can be managed. It simplifies the handling of growing data structures. Programs can be altered and recompiled independently without requiring an entire set of programs to be relinked and reloaded, which certainly saves time. And you can share amongst processes. And it also has abilities to have protection. So paging is efficient, but it doesn't give as much control to the programmer as segmentation. So let's look at how this gets accomplished in a couple different architectures. And first, we'll talk about the Intel x86 memory management. And this is based upon mainframe experiences. The x86 architecture has both segmentation and paging, and the user can choose from 4 different views of memory. You can have unsegmented unpaged memory, unsegmented paged memory, segmented unpaged memory, and segmented paged memory. Now let's take a look at each of those. So unsegmented unpaged memory, the virtual address is the same as the physical address, and this is low complexity, the easiest solution, and it's useful in low complexity, high performance controller applications. Unsegmented paged memory, the memory is viewed as a page linear address space. Protection management of memory is done via paging, and that's favored by some operating systems like Berkeley Unix. Segmented unpaged memory, the memory is viewed as a collection of logical address spaces. It affords protection down to the level of single byte, guarantees that the translation table needed is on chip when the segment is in memory, and results in predictable access times. Segmented paged memory, segmentation is used to define logical memory partitions subject to access control, and paging is used to manage the allocation of memory within partitions. Operating systems like Unix System 5 favor this view. So in terms of segmentation, the x86, each virtual address consists of a 16-bit segment reference and 32-bit offset. The unsegmented virtual memory is 4 gigabytes, segmented virtual memory is 64 terabytes, and the physical address space is 4 gigabytes. The virtual address space gets divided into 2 parts. One half is global, that's shared by all processors, and the remainder is local and distinct to each process. Associated with each segment are 2 forms of protection. One is privilege level and one is access level. And there are 4 privilege levels, one for most protected, which is level 0, to least protected, which is level 3. Privilege level associated with the data segments, its classification, and privilege level associated with the program segment is its clearance. An executing program can only access data segments for which its clearance level is lower than or equal to the minimum privilege level of the data segment. The privilege mechanism also limits the use of certain instructions. So let's take a look at how ARM deals with memory and or memory management. And virtual memory in ARM is quite versatile. There are 1 or 2 levels of tables for translation from virtual to physical addresses, and the translation Lookaside buffer is a cache of recent page table entries. Data gets exchanged between the processor and memory via the cache, either logical or virtual. And ARM supports memory access based on either sections or pages. Super sections are optional. These are 16 megabyte blocks of main memory. Sections are 1 megabyte. Large pages are 64K, and small pages are 4K of main memory. Translation table is held in main memory has 2 different levels. Level 1 holds descriptors that contain the base address and translation properties for a section and supersections. Translation properties and pointers to the level 2 table are also held for large page or small page. Level 2 descriptors contain the base address and translation properties for a small page or a large page, and these require 1 kilobyte of memory. For ARM access control, control bits in each table entry give control access to a region of memory by a given process. A region of memory can be designated as no access, read only, or write only. And the region can be privileged access only, reserved for use by the OS and not by applications. ARM employs the concept of a domain for access control, collections of sections and or pages to that particular access permission. The ARM architecture supports 16 domains and allows multiple processes to use the same translation table while maintaining some protection from each other. There are 2 kinds of domain access that are supported. One is for clients, and one is for managers. So that's it. Thanks so much for watching.